Hello and welcome to another video on orbital mechanics. I'm going through the book Orbital Mechanics for Engineering Students by Howard D. Curtis, and I'm on to problem 1.14. Problem 1.14 is still on relative motion and time derivatives of moving vectors, and this question is asking about a car on the surface of the Earth traveling north at a constant speed of 100 kilometers an hour, and it weighs a mass of 1,000 kilograms, and it's starting off from 30 degrees north latitude. This is the picture here. This is the car. This is the direction it's traveling. This is the Earth. This is the Y axis. The X axis is going into the page. The Z axis is going up. The car itself has its own set of axes around it. So it's got the lowercase k going out this way, and then it's got the J axis going around here, and it's got the X axis going around the Earth, perpendicular to the other axis. So that's the moving frame, and then this is the inertial frame for the Earth. Now the equations to figure this out are sort of the same as before. You plug in your numbers and you get answers. The derivations for those are quite long-winded, but it is more or less more of the same. If you go through the page 31 in the book, or from page 29 to 32 in the book, slowly, you can work out all the derivations for these equations. Just takes a bit of time. I'm not going to go through it now. I've done quite a bit of that already. There's a series of equations provided on page 32 that give you different scenarios. And the scenario we're looking at is essentially the flight due north at constant speed and altitude. Now our altitude is 0. We're on the surface of the Earth. So our equation for velocity is just the angular velocity of the Earth, the radius times the radius of the Earth, times cos phi I, not the I, plus velocity j. That's the y dot is the velocity. And the velocity is, well, 100,000 over 3,600 meters per second, and the angular velocity of the Earth is 2 times pi for one complete revolution divided by the number of seconds in a day. So that's what that is. So we know this, we know the radius of the Earth, and we know phi is 30 degrees, and we know the velocity, so we can plug that in, we can get the velocity. The acceleration is -2 angular velocity of the Earth times the velocity of the vehicle times sine phi I, and the angular velocity squared times the radius of the Earth sine phi cos phi j minus the velocity of the car squared divided by the radius of the Earth, the vertical velocity component, this bit here, plus the angular velocity squared, radius of the Earth, cos squared phi. When you plug all that in, you get a value for A, well, a vector. And then to get the force that's being, what's it asking for is the lateral force on the road, on the car. So, the Earth is spinning, right? And that spinning component, the car is just driving north. So all of the eastward or westwardly force that it's experiencing is from the rotation of the Earth. So after we do the mass times the acceleration, we just take the I component, and that's the lateral component, and that's minus 2.026 newtons, which is left, right, west, and that's right. And then the normal force of that is, well, so the actual movement of the car generates a centripetal force that acts upwards. So that's that A there. AZ is actually negative. So we get the force of the gravitational acceleration plus the acceleration Z component, and we get a value that's just slightly less than 9.81. And so then the net force, the net normal force, is 9,784.4 newtons. That's all good. There's not much else to say. I'm going to put a MATLAB script in the description. If you have any questions about any of the derivation in the book, please ask. It is quite long-winded. And that's all. Thank you very much. Bye-bye.